Thanks for the introduction. Am I audible and can you see my screen?
Yes.
Okay. First of all, thanks for everyone for coming. I see there are more than 100 people here who are still there for the last talk of the day. So thank you for sticking around. And thanks to the organizers, especially to Praveen and Venki for inviting me and to organize this event in honor of Vasu. As a student of Vasu, I can say he was somebody who truly cared about not just everyone who worked with, but also his students. So I did my master thesis under his supervision many years ago. And it was his words of encouragement, his words of motivation that even put me into academia, that made me go on to do a PhD. So to a lot of ways, I owe my career to him. And I know that many other people here have been very greatly impacted by him in different ways, and he will definitely be missed. So today I'm going to be talking about mesh-free methods for fluid flow modeling, and I'll also go quite a bit into applications done with industrial partners in the automotive industry. Before I start, I must acknowledge a lot of collaboration, a lot of people whose work has gone into this talk, both at my current position at the University of Luxembourg and at my previous position at the Fraunhofer Institute in Germany. And this is only, I've listed out people who have contributed for the simulations, but there are a lot of more people who have helped us in experiments, which has led to everything that I'm talking today. And of course, I have to acknowledge funding from the DFG in Germany, from the European Commission's H2020 program, and from collaborations with several automotive partners. I'm only listing two here because this talk is being recorded and I do not think I'm allowed to list the others. A brief outline of my talk. First, I'll be talking more from an applied engineering perspective and not an applied mathematics perspective. I'll try to give a general overview of why mesh-free methods are needed, what are the good things about them, what are the bad things. Then I'll talk a bit about mesh-free collocation, which is a specific type of mesh-free methods, about how they can be used in Lagrangian frameworks, and then I'll go on to actual applications. One more caveat to say before I start is that there are many, many different mesh-free methods, and everything I say today will apply to different mesh-free methods to different extents. I'm specifically focusing on mesh-free collocation, but most of these ideas will apply to other mesh-free methods as well, but just not to the same extent. So now, why do we need mesh-free methods? The biggest reason that, at least that you will hear of, is that you avoid the task of meshing. So here I'm taking an example of generating a discretization around a car. It's typically much easier to just generate a set of scattered nodes in the domain rather than generate a structured or an unstructured mesh for that matter. Now this becomes especially relevant around complex geometries. So if you look at the figure on the right and you see the underbody of the car, here you have a lot of complex parts which need to be represented exactly. And it's these regions where really a point cloud representation is a lot easier than a mesh. One note on terminology is you will see a lot of different words used. You will see points, you will see particles, and you will see nodes. These are three terms commonly used in mesh-free methods. For the purpose of today's talk, these three are the same. There's no difference between them. Each of these points, I will use points, but can also be called particles or nodes. Now, a second big advantage in mesh-free methods is that connectivity is much simpler. I do not need to store proper connectivity as you would in a mesh. All you need is for every point, you need a set of neighbors or a compact support over which you will perform all discretizations. So here, for example, this support is based purely on distance, that I say all points within a certain distance will be counted as my support domain. In other notions, you can also say I want the closest endpoints, which will work in a similar way. Now, this neighborhood is what will be used for all derivative computation, for all approximations that you're doing. Now, a third advantage is the ease of representing simulations with large deformations. So on the right, you see a case where you've put these dummy domain with the CFD letters and you heat it from the bottom and it starts melting. And if you were to do this with a mesh, you would need to extensively remesh the entire domain to capture the changes in the geometry accurately, which is much simpler in a mesh-free method. I will go on to more detail about remeshing later on in this talk. And we'll already come to the first application for mesh-free methods is this water crossing. So we're considering a car moving through a shallow region of water, and we want to check what is getting wet and what is not. It's an application I will talk about in more detail later. Why is this challenging in mesh-free methods is one, you would need to mesh an entire domain where the fluid could flow. Whereas if you were to do it with the mesh-free framework, you only need to discretize where the fluid is and not the entire domain. Moreover, the car is moving, not just in a linear way, but you will see wheels are rotating. You could have a suspension that makes the car go up and down, all of which would make remeshing to be quite expensive. Now, closely related to the advantage of capturing large deformations is free surface flow. So any simulation where you have a free boundary that's moving, the advantage of why mesh-free methods is important for these kind of applications is that you don't need to do anything extra to track where the surface is going. A Lagrangian framework comes pretty trivially with the mesh-free method. They go together very well. So it's easy to just capture your advection with the moving particles or points themselves. A last advantage that I talk about today is on adaptivity. So this can be thought of in two terms. One is having spatially varying densities for your discretization, which is reasonably easy to achieve. But a lot more important is on adaptive mesh refinement, so to say, adaptive point cloud refinement. This is in many ways much simpler with a point cloud than a mesh, because you don't need to worry about notions of non-conformativity or hanging nodes and things like that. You can simply add points wherever you need to, or delete if you need to coarsen, and that works quite well. Now, there's a saying that Vasu used to like to say a lot, that there's no free lunch. It's not that when mesh-free methods have these advantages that they are the best numerical methods ever. There's a lot of disadvantages that comes with them as well. Especially given today's audience, a lot of people here are doing a lot of theoretical work. And for that audience, a very important reason why mesh-free methods are not so good is an absence of formalism. So it's really hard to prove things in mesh-free methods. In most cases, people have been unable to prove error estimates, have been unable to prove convergence or get bounds on your solutions and things like that. While that is slowly changing, people are slowly trying to do this in mesh-free methods. It's still far, far behind what you can do in finite elements or finite volumes. And most work that's even being done today only holds on the structured point clouds that you see on top, and the theory does not hold on unstructured point clouds, which is what you need to capture all the advantages that I spoke about. So this has actually led to, let's say, a fair amount of skepticism because of this lack of formalism. Now, a second disadvantage that's usually neglected in mesh-free methods is a lack of conservation. Now, what do I mean by this? Let's say we are solving the conservation law on the right. Now, if we were to discretize this with, say, a finite volume method, you know that in your finite volume framework, you have a discrete notion of a Gauss theorem, which means that if I consider the flux between adjacent cells, I know that it is equal and opposite. So if I go from cell 1 to cell 2, it is the negative of what I see from cell 2 to cell 1. And because of solving your conservation law and having a discrete Gauss theorem, you know you get a notion of global conservation. So for example, of conservation of energy, if that's what you're solving. Now, this is something that's often taken to be quite, it's assumed and it's taken to be a given in finite volume methods, but this is a big challenge in most, if not all, Meshfree methods. Because of the local nature of the approximation, because of a lack of a global discretization structure like a mesh, you do not have any notion of a Gauss theorem at the discrete level. As a result of this, no matter how accurately you solve your conservation law, you cannot get any control over a global notion of conservation. So a lot of people in the last, I'll say 7 to 8 years have tried to reduce this drawback, but as of today, it's not possible to truly overcome it. You can just come up with partial solutions that can prevent this. There are a few other disadvantages that are specific to different Meshfree methods that I won't go into, but linking to the previous speaker, another challenge is talking about ensuring positivity is also not so trivial, and a lot of extra work needs to be done for that. Just some context now before I move in as to what am I solving, what are my governing equations. For a lot of what I'm doing, I'll only be talking about Navier-Stokes, but in general, I will talk about the classical conservation of mass, linear momentum, and energy. Depending on the kind of model being used, you may have some additional equation of state. For example, if it's a compressible, if you have a compressible flow, you need some equation of state to close your system. And we are essentially using the same kind of system for also modeling solid flow, so to say, deforming solids. So your stress tensor that you see in the momentum and the energy equations will also have a solid term which can be governed by different models. For example, a Johnson-Cook model or a Drucker-Prager model for sand or something like that. Now I'll come to how do we discretize derivatives. So Meshfree frameworks naturally have both strong and weak formulations. Today, I'll only be talking about strong form Meshfree methods or collocation methods. Most of these have some form of moving least square type approximations. Now, strong form Meshfree methods are generally broadly classified into 4 categories: radial basis function, reproducing kernel, and discrete correction of particle strength exchange. Today, I'll be focusing on GFDM, which is essentially, as the name suggests, it's a generalized finite difference method. So it generalizes classical finite differences to unstructured point clouds. Now, there are a lot of different Meshfree methods that I've listed here that are very similar and can essentially be classified under the GFDM umbrella. And most of what I'm talking about applies to all of these. So the idea is what I already said, that you will generalize the notion of computing stencils from structured grids in a finite difference case to unstructured point clouds in a GFDM case. Now, when you have these unstructured nodes that you see on the left, it's not possible to write out stencils analytically, on paper. If you were solving a classical finite difference and you say, I have a 5-point stencil, you can derive derivative coefficients on paper and you don't need to do anything computationally. In the Meshfree framework, you need to actually compute this also from a numerical perspective. You cannot do it on paper. But the basic idea is the same, that any derivative is represented by sum of the function values at these neighboring points weighted by some coefficients. Now, as is the case in classical finite difference, you can do this by minimizing the errors in truncated Taylor expansions. So we'll write a Taylor expansion around the center point on each of the neighboring points and minimize weighted error summations. You can also write the same formulation in an equivalent way, which is for some people may be easier to understand, is that I have a set of test functions here referred to as P, which you will differentiate exactly. So if you want to link this with the Taylor expansions, you can say, I will differentiate a set of monomial functions exactly. And typically the number of monomial functions in this test space is lower than the number of points in your neighborhood, which means you have an underdetermined problem and you solve some sort of a norm minimization procedure to get your final stencil coefficients. Now I want to go on to the Lagrangian framework. So you can essentially think of only incompressible Navier-Stokes for now, although this idea applies to a more general modeling that I mentioned earlier. So one thing you need to do is move points with the fluid velocity. That's how you would do it in a Lagrangian framework, even with a mesh. The other notions of how to solve for the velocity and pressure is something I won't go into details for today. I want to focus mainly on what this movement leads to. Now, naturally, when you're moving a point cloud, as that happens when you're moving a mesh, you will get distortion. In a mesh-based method, this distortion is very well known, which is why pretty much nobody uses truly Lagrangian mesh-based frameworks. In a point cloud also, of course, you will get this notion of distortion, but the advantage is that it's much easier to fix this distortion. Now, how do we do this? You can split the distortion into two kinds. One on the top is, you see the presence of a hole where I do not have any points, and I need to identify the holes. There are a lot of people who have worked on hole identification algorithms, where you identify where no points are and add points, and you get this result on the right. Now, why is this easier than what you do for a mesh-based framework? Is that I'm not affecting anything globally. This is a purely local procedure. The points you add in the center here are not affected, do not affect the points outside, which is not always the case in a remeshing, where you may need to do a global procedure. And the other kind of distortion is where points come very close together, where you can simply merge them into a new location. Of course, while both doing addition and deletion, you will have to reapproximate all physical values at these new locations where you're either adding points or merging points. One important point to note here is that in the context of mesh-free collocation, this is very easy to do because each point here is only a location where we are approximating or solving our PDEs. It is not a mass particle, as is the case in some mesh-free methods like SPH. So it's quite easy here to add and delete particles to fix distortion. Now, these notions of filling and thinning can, of course, as I said, be used to fix distortion. An example here is a simple surface that I'm stretching in different directions. And you can see that the number of points discretizing the domain goes up by a factor of 1.5, can be larger in some cases, and can go down pretty easily. The same notion of thinning and filling can also be used for adaptive refinement. So this is an example of a metal cutting simulation. All you need to do is, once you identify locations that need refinement, you tag those locations saying, okay, I need a smaller discretization size here, which will automatically trigger your whole identification algorithms and will add points where you need to. So now let me go to a few different applications of Lagrangian mesh-free collocation. All of these applications are done in collaboration with several industrial partners. I'll be talking about 4 broad applications: fuel sloshing and tank filling, water crossing and rainwater management. The 2 applications on the left, that sloshing and filling, are applications where you still see a lot of people use finite volume frameworks with with a VOF method. However, in the applications on the right, today it's close to impossible to do these applications with a mesh-based framework within a reasonable amount of time. But before I come to the applications, there's one very important point to note is how do we make sure that the methods we're using are actually producing correct results? It's very easy to consider academic test cases. I've just listed a few here that are common for incompressible flow problems. There are many more for different scenarios. But these academic test cases do not go to verify or validate your work on actual applications, because there's a huge gap between them and actual applications. So for each application, I'll talk a bit about what we have done to validate it, how we have done that. A starting example is a classical benchmark problem, which is now being studied a lot in the last, let's say, 15 years, is a dam break problem. So you have a layer of fluid that collapses, and you have different, in experiments, they've put different pressure sensors in different locations, and they measure, so these green points that you see, they measure what is the pressure there, they measure what is the height of the fluid and things like that. And this is the first comparison at 2 different sensors where we see that the numerical result matches the pressure very well at the bottom and the fluid height pretty well at the top. The first application that I'm going to be talking about is fuel sloshing. So sloshing is essentially, imagine I have the fuel tank in your car. Now, when you accelerate, the fuel will move around because obviously your tank is not 100% full. Now, when this moves around, this is the video you see on the right, you can have many adverse effects. One is if it's causing a large forces on your tank, you can have structural damage to the tank. Second is you can have a lot of noise in some situations. Now, this problem is really exasperated for large fluid transport. So if you think of these large oil tankers that transport oil in large distances, for them, this problem can truly affect the safety of moving the tanks, because when you're doing a steering maneuver or when you're doing sudden acceleration or braking, the impact of the fluid on different sides of the tank can cause instability in the vehicle. So for these problems, it's very important to put breakers or baffles to reduce the sloshing, and we need simulations to truly decide where to put these barriers. Now, to validate this, we start with a simple case of sloshing in a cube. So we were not considering the geometry of the tank itself. And you can do this with different frequencies of rotation. So you see on the right that you just have the tank being rotated at a particular frequency, and then slowly you increase the frequency, which is not shown in this video, and you do the same thing numerically and try and correlate the results. This is the first level of validation. And the second goes to doing it actually on real geometries. So the figure on the right is a tank in an actual car, and our partner has done experiments where they have measured pressures at these 4 locations. My apologies, this is written in German. And they give us, we get the geometry from them and then try and run the same sloshing simulation on the real geometry and examine what the numerical pressure is and compare it to the analytical pressure. So this is the first results of that. The dark blue line is the experimental results. 0 pressure here means that there's no fluid at the location of the sensor. And we try and do different simulations and get pretty good correlation. One important point here is that you have to do, especially for these sloshing simulations, you have a certain amount of non-determinism in them, in the sense that sometimes a small change in the initial condition or in the boundary condition can make a large change in the solution. So it's to a certain extent even ill-posed. So we kind of need to break up the simulation into an average and a fluctuation part. You could, in other sense, do this in a stochastic way, which we have not considered. But the idea is that finally you get a pretty good comparison between simulation and experiment. Now, related to sloshing is the second application is on tank filling. So this is when which you see on the figure on the top right, you're actually filling fuel into your fuel tank. Why do you need this simulation? Is that you want to try to measure things like spitback, which is it happening that fuel is coming back before the entire tank is filled? You see a simplified example of that on the video on the right, that due to pressure changes inside the tank and due to the geometry of the inlet, it happens that your pressure outside and inside equalizes before you can fill the whole tank, and then you just get fuel overflow and you're unable to fill anymore. So these simulations of this are used for checking the design of the inflow channel of the fuel chamber itself. Now I go to another application which I talked about right at the start, which is water crossing. So why are we doing these water crossing simulations? Is we want to check where does the water go below the car. So for example, you have an air intake. You don't want water to go under an air intake, into an air intake. These simulations today are very important for most automotive manufacturers. In Europe, especially, most manufacturers now necessitate these kind of simulations where you want to check what happens when you take a car, make it go through a pool of water of a certain thickness at a certain velocity. Can the car still function? And of course, doing experiments for this is extremely hard because they need to keep rechanging the design of the car. So it's much cheaper to do simulations. Now, validation for this was something that was extremely hard. We had a collaboration with Volkswagen where they drove a car into a pool of water and truly measured everything that they could. You measure wind conditions, you measure temperature conditions, you measure how all of that is around the car, and we try to reproduce that in our simulation. The actual geometry of the car is also what they gave us of the same car that they ran through the water. Now you can see this from front and from back, but this comparison it's really hard to say anything from this comparison. Is the picture on the left the same as the right? It's hard to truly say. So what Volkswagen did was they took our simulation and put it on top of the experiment, which is the video you see on the left. So the blue points, which you can see more clearly in the zoomed in version on the right, is the simulation. And of course, the actual water that you see is they've got from their high-speed camera in their experiments. And you even see the overlay of the car geometry itself on the real car. And you can see this quite clearly, especially on the right, that we observe a pretty good prediction of the waves of the car, of the water around the car. And what you don't see here is that we also observe really good correlations on what happens below in the underbody, which is the main concern here. A last application that I want to talk about is rainwater management. So this is about rain falling on an automotive. And what you want to check is where does the fluid flow? So on the right, we don't show the rain in this video. We only show it falling on the vehicle. and you want to show where is the water moving. Originally, you wanted to check whether this is moving into things like the A-pillar and it's not going into the car. But today, this is becoming more and more important as we move towards self-driving cars. Manufacturers are putting sensors at different locations on the car exterior, and we need to do simulations to make sure that water does not collect where these sensors are, which would affect how these sensors perform. Now, one last example is I want to present a particular challenge that we are trying to manage. Going back to the water crossing example, what you see is in many cases, especially at the early stage of it, so what you see in the blue and the yellow points, is that the water is in very, very thin layers. So now if we come back to this point cloud picture on the top right, I had said earlier that we are looking for each point. So here for the red cross, we're going to compute approximations based on the points in the neighborhood in this black circle. Now, if you want to have a certain set of test functions that you want to differentiate exactly, you need a certain size of this neighborhood. Now, when I have very few points nearby, it's not possible to get enough points in a neighborhood to truly get the order of accuracy you want. So what this figure actually shows is regions where we had to decrease the order of accuracy. We start in these pink regions where we are saying we want to differentiate quadratic functions exactly. Then we go on to a lower order in the yellow region and an even lower order in the blue region where you're only reproducing constant functions in derivative computations, which is obviously not very accurate. So towards this, to fix this, we are trying to work on developing different kinds of thin film models. So existing thin film solvers like the shallow water equations are currently not able to solve these kind of applications for many reasons. And we're trying to work on developing different models that can be coupled with these thin films with bulk regions where I can solve full 3D Navier-Stokes here and a thin film where I currently have the blue and yellow points. So yes, I would like to end there. As I said, there are several advantages for Meshfree methods in certain cases, but I do not want to pretend that this is the perfect numerical solution. In many situations, it is not the right choice. For example, even in the automotive industry, when you talk about aerodynamic simulations, which is a key concern, today Meshfree methods are not at all competitive with finite volume methods, because you have a situation where the geometry is relatively simpler because I'm only interested in the top of the car. Yes, you will have some sharp edges, but it's not as bad as the bottom. You will typically have a stationary vehicle in your wind tunnel tests, and things like turbulence modeling is a lot better understood with a mesh framework. So in a lot of scenarios, Meshfree methods still lag behind a lot. And I also just want to point out, if you want to see more applications, either from a scientific side or from an industrial application side, you can see it at these two links. Most of the applications I've done are with the Fraunhofer Institute and their in-house software Meshfree, which you can find more information about here. Since this talk is being recorded, if anybody wants to read up more on the solvers that are behind these applications, the spatial discretization, the temporal discretization, these are a few papers of our group, but I would like to point out that none of these actually go into the application because most of that we are not allowed to publish because of NDAs. And thank you for your attention.